So for the last lesson in equilibrium, we're going to relate this standard Gibbs free energy to the free energy not under standard conditions. When you're doing homework or you're working on a test or quiz, you really got to read carefully and remind yourself whether the question is about standard conditions or whether it's about the free energy not under standard conditions. We've got a Q back that we haven't used in a long time. This isn't the Q from heat, it's back from the Q from equilibrium. So if we had a reaction A plus B equals C plus D, okay, just reminding you of writing equilibrium constant, okay, we would write the equilibrium constant as concentration of C times D. If we did have a power, so if there was two A's in this reaction, A would show up squared. We're using Q, so it's the exact same ratio. I'll leave the square in. But we're under initial or any condition, so often a not symbol is put in to represent initial conditions, okay? But again, it doesn't have to be initial. It could be the reactions run for 10 seconds and you want to know if it's going to be spontaneous anymore. You could put in the values at 10 seconds and you'd still have a Q value. Let's talk a little bit about the magnitude of Q, the sign more so than the size. Okay. What if you have a low percent reaction? Okay. So if you have a low percent reaction, you're not going to have much C or D. You're going to have very little product, so Q is going to be quite small. You may want, and it's going to be much less than 1. Often we looked at whether Q's were bigger than 1 or less than 1. Okay, we're not going to do the exact same thing, but still think of small as being, a small decimal. Okay. So if Q is small, what's going to happen to this term? Okay. If you take the negative log, if you take the natural log of a small number, you're going to get a negative output, okay? And there's no other negatives in this in the underlying green piece. R, the universal gas law constant, is always going to be positive. Temperature is always going to be positive. So when you have small q's, the RTlnQ is going to be negative. Okay? And we think of what makes a reaction exergonic or spontaneous, we need a negative delta G. So when we are at the very beginning, we have very little amount of product, we have a lot of reactants, that green piece is likely to be negative. And the earlier you are in the reaction, the more negative it is. Versus if you have a high percent reaction, okay, or just a lot of products, everything's going to flip. Okay. Q is going to be relatively large. Could be 100, 1,000, 10,000, could be 100 million if you're close to 99%. Now RTlnQ is going to be positive, and the more you are towards products, the more positive it's going to be. Okay. So this percent of reaction is going to modify the value we have from standard free energy. Okay. This free energy could be positive, the standard, delta G naught could be positive, and we can get a reaction to proceed as long as this piece is negative enough to swamp it and overcome it and drive the reaction. So even though a reaction might have a positive standard value, okay, there are conditions that the reaction will still go forward. We're going to kind of talk about those conditions and do some calculations with it. Last bit of this intro slide. Equation 1 can be used to determine equilibrium constants. Okay? I find this really neat. Teaching regular chemistry 30, there's no connection between the units. In AP, we're going to make big connections between our equilibrium unit, the thermodynamics unit, and when we do electron exchange or electron transfer, and we figure out voltages of a cell or a battery, you can relate that voltage to free energy or an equilibrium constant. Everything sort of comes together. So let's see that with two of the units. So if you're at equilibrium, I'm going to repeat that equation. The free energy you have under non-standard conditions is the free energy under standard conditions, RT ln Q. Now we're going to be at equilibrium, so I'm going to modify that. If we're at equilibrium, what is the free energy? There's no free energy at equilibrium. It's no longer spontaneous. So delta G equals 0. Okay. The standard state value isn't going to change. This is a tabulated value. Okay. And again, this can be confusing, keeping it straight that the delta G is going to vary where the standard one doesn't. Okay. That's tabulated. That's what you're going to find in data tables or added into an exam in a little table. Plus RT natural log. I'm not going to write Q now. What am I going to write at equilibrium? I'm going to write K. Okay. And that's our relationship we can relate delta G to K. There are only two variables, assuming temperature is a constant. And we're going to use two forms of K. One you're really used to, K for concentrations. Use this all through chemistry 30. Okay. We need to use moles per liter. You can also have equilibrium constants with pressure for gases. Everything is done the same. You write the equilibrium law expression the same. Okay. Okay. So don't get confused if you see a KP instead of a KC. You're just using different units. Okay. So we're going to dive next sort of back into looking on a number line about when reactions are going to be exergonic, but from a perspective of equilibrium constants or Qs. Okay, so we're going to look at two possible outcomes if you have a really high equilibrium constant, so much greater than 1, and then below we'll look at small equilibrium constants. I'm going to color code this, so if you do have multiple colors, it can be handy to make the positive values one color and the negative another, but you certainly don't have to. This number line is going to be a percent reaction, and I'll talk about the delta G standard and delta G at that particular point. So this is the equation that's going to let us predict delta G on the bottom from the standard. Okay. We have a really big equilibrium constant. That's our theme. So percent reaction-wise, this reaction's gone really far forward before we get to the point that delta G is 0. Okay. This is the point where Q equals K. Okay. And we've got a really big K, so we're really far product forward. In terms of our sign of delta G naught, you're going to find that delta G's, when equilibrium constants are really big, are always really negative. The bigger the equilibrium constant, the more negative it gets. So we haven't done any math with it, but it's coming from here. Okay. The larger the K value, the more negative delta G would be when you solve for it. Okay. So delta G, that's a standard value, is always going to be negative, okay? No matter where we are. It's a constant. Okay? So this delta G, because we have a large K, is always negative. It really wants to make this reaction exergonic in most conditions. Now, if we think about at the very beginning of the reaction now, we're going to calculate the free energy at different points on this line, at different points of reaction, and we're going to start at the very beginning, okay? When the percent reaction is maybe not 0, but slightly more than 0. When the reaction is slightly more than 0, okay, that piece, okay, Q is really small. The natural log of a really small number is negative. So this whole term is going to be negative, okay, at the very beginning. Okay, so that's going to keep delta G negative. I'll just add in that statement. You may not want to add that into the number line, but I want to get a visual for what I just said. Delta G is negative. Delta G standard, sorry, is always negative. The RTlnQ piece is still negative, so our reaction is still negative. As we start increasing the percent reaction, Q, the ln Q is going to get less negative. Okay? So as we work along, this will be smaller. Maybe I'll just write it smaller so you have a hint visually. Okay? But we still have two negative pieces, so we still have an exergonic reaction. Okay? And hopefully you're starting to see the trend. As we go further along our percent of reaction, this is going to get smaller still, and eventually, the magnitude of the negative will get smaller, and eventually the Q, when you get maybe past the halfway part, the log of Q, natural log of Q will flip to be positive. As Q starts really small, gets less small, heads towards 0, and eventually when you're well above 50%, it's going to flip positive. So at some point, it's going to flip positive. Okay? Maybe Q is 10. So you take the natural log of 10, that's a positive number. RTln, a positive number, will be a positive number. Okay. But the delta G is still bigger than the RTlnQ. So you can still have an exergonic reaction because delta G standard is just so big. Okay. And then at some point, the RTlnQ will get big enough that it's exactly the same magnitude as delta G standard. So if delta G standard is minus 100 kilojoules per mole, eventually the RTlnQ will be positive 100 kilojoules per mole. They'll balance each other out. And then if you go past the equilibrium point, RTlnQ will be really large and positive, in which case delta G will be large and positive and will not happen. So we've got a lot in this number line. We're going to do it again under low equilibrium constants. You'll get a repeat. Okay. So what's driving the reaction all the way through the beginning? It's the delta G is just so large and negative. It's driving the reaction kind of no matter what the reactants and product ratio is. We have a negative free energy. So that's going to drive the reaction forward up until you get to the Q equals K. At that point, the two pieces have canceled each other out, delta G standard and RTlnQ. Okay? If you dumped in a huge amount of products and you started way out here, okay, where Q is so big, RTlnQ is so big, the reaction doesn't happen. It'd be endergonic out here in the forward direction, but out here the reaction would actually want to go backwards. If it's endergonic forward, it'd be exergonic in reverse. So this is kind of what we get for free energies. It's no different than what we would have said in the equilibrium section. Okay, if you have a Q well below K, the reaction is going to go forward. If you have a huge Q that's past K, so your Q is out here, okay, you dumped in a ton of products, the reaction would go in reverse. Okay, and we saw that, and hopefully everybody saw this in a lab situation. Okay, so low equilibrium constants, now they're greater than 0 because they can't be negative, but they're much less than 1. So we'll look at delta G standard. I'll add in RTlnQ. When equilibrium constants are really small, okay, maybe 10 to the minus 5. That was a pretty common equilibrium constant that we saw in the past. If you use this equation to solve for delta G, when K is, let's say, 10 to the minus 6, you're going to get a positive value for standard free enthalpy change. Delta G standard is going to be positive, and that's a constant. No matter where we are on this percent reaction line, it's a constant. Okay. But what we can't infer is the reaction is always endergonic. Okay. There are some circumstances. If you have enough reactant, the reaction, or a lack thereof of product, a lot of reactant, the reaction can occur. So just to give you a visual of the map that I just mentioned, I'm going to rearrange what was on the bottom of the previous slide. And delta G standard is minus RTln K. So when K's are really big, you get a negative delta G. When K's are really small, you get a positive delta G standard like we have here. So the equilibrium point is going to come really quick in the reaction, okay? Potentially almost right on top of my vertical black line. I'm just going to give myself a little room for writing, okay? This is the point when K's are really small. You're going to get to equilibrium really fast in terms of percent reaction. This is where Q is equal to K, where there is no more free energy. Okay, I'm not talking about delta G naught. Delta G is now 0. So same as before, at the very beginning when Q is almost 0, it's really tiny, RT ln of a tiny number is going to give you a negative number. The less the reactions proceeded, the more largely negative it's going to be. So at the very beginning, we have quite the large negative RT ln Q. Trying to emphasize that it's really big. And really only at the very start of the reaction is RT ln Q so massively negative that we get an exergonic reaction. Fairly quickly into the reaction where Q is equal to K, okay, delta G standard is, it's always positive, and it's not long before the RT ln Q piece ties it. Free energy goes to 0, and the reaction stops. If you look at percent reactions much past equilibrium, okay, you know, if RT ln Q is positive, okay, because delta G standard is positive, the free energy is just going to be positive, and it's just going to stay positive. It's just going to grow more and more positive, more and more endergonic. So when equilibrium constants are small, we only get an exergonic for a very small piece. realize on a number line, I've really overblown this up, okay? This piece maybe should be a millimeter in width if the equilibrium constant is 10 to the minus 6, okay? But I blew this out sort of out of scale to right. Okay. For the vast majority of time, you get a endergonic reaction in terms of where we are on a number line, but you get exergonic in the reverse. So we're just going to finish up. We're going to use those equations. I keep talking about doing, you know, when the signs are positive, negative of RTlnQ, or when we get a positive or negative delta G standard. Let's do a little bit of math to wrap up this section, okay? But we're going to think about the result. When we get an answer, we're going to know something about the equilibrium. We're going to know something about whether that reaction is going to proceed forwards or backwards. Okay? So our answers aren't going to be, oh, this reaction doesn't happen. Potentially, it might be that it's going to go backwards to the conditions given in the question. Okay. So first question, again, I find this fascinating from a nerdy science point of view. What is the equilibrium constant? And we're just going to use thermodynamics to get there. Okay? A concept that doesn't seem linked. How does heat transfer and disorder and chaos relate to equilibrium constants? Well, it does. The calcium hydroxide, we're going to put it into water. And if we can figure out the standard delta G, we can figure out the equilibrium constant. So we can look up delta G of formation values, standard ones. Okay. And I used Chang version 11 to grab these numbers. The formation of calcium hydroxide solid, the Gibbs formation value, minus 896.8 kilojoules per mole. For calcium ions, minus 553.0 kilojoules per mole, and hydroxide, minus 157.3 kilojoules per mole. Okay. And in a previous lesson, we learned how to figure out the delta G for this reaction. Products minus reactants, the same thing we did with enthalpy, so I'm not going to write that math out. When you go products minus reactants, factoring in that there's two hydroxides, I get a positive 29.2 kilojoules per mole for this reaction with those stoichiometric constants. And this, which I just predicted from tables, is all I need to figure out the equilibrium constant. Okay. So now we're ready to get that equilibrium constant. So delta G equals minus RT ln Q. That's from the bottom of the first page. I just hadn't rearranged it. We had 0 equals delta G plus RT ln Q from our first slide. Okay. Okay. So I rearranged that for delta G. Okay. So we've got to do a little math of natural logs. We use natural logs in the rate of reaction units, so our skills, I think, are a bit better. So I'm going to rearrange. I'm going to get ln Q by itself. So delta G standard, I'm going to move over the RT. And I'm throwing in Q, but we're at equilibrium. So I wasn't sort of wrong, but I was incomplete at equilibrium. I should have put in K. How do we get rid of a natural log? That's where we had to use a base of E. If it was a regular log, you'd use a base of 10. But we're going to raise each of these to the power of E. E to the natural log of K, that cancels out. So E is Euler's number. So I'm going to sort of flip the sides. K is isolated on the right. I'm going to write it on the left. And we have E to the minus delta G naught over RT. That's how we're going to get the equilibrium constant. So we're going to start plugging things in. Delta G, we just predicted it, 29.2 kilojoules per mole. I'm going to write everything in, and then we'll look at our units. R, the universal gas law constant, go to your AP formula sheet, 8.314 joules per Kelvin per mole. And our temperature under standard conditions is 298 Kelvin. So we're figuring out the KSP, a standard condition. Our units don't match here. I've got kilojoules on the top, but joules on the bottom. So I'm going to convert kilojoules to joules. Doesn't matter. One of the two you had to convert. So I want to get rid of kilojoules on the top and get joules. 1,000 joules is exactly 1 kilojoule. Don't do sig figs with this 1 kilojoule. That is exactly 1. Now everything's going to work out. Kilojoules, kilojoules, joules, joules, Kelvin, Kelvin, moles, moles. Good, because there shouldn't be any units to a constant, an equilibrium constant. And I get 7.6 times 10 to the minus 6. Now this is a solubility, so I could go KSP. We talked about KSPs. So now in theory, we did the solubility of this exact chemical early in the year. You didn't need to look up the value. You could have predicted the value if you wanted for your percent error. Okay. So our last example, going to tie in the Q part, do some math with it. The KP, so we've seen KCs before. This is just a constant, but using pressure values. So the K for the production of ammonia is something times 10 to the minus 4, so pretty small K value. Okay. We're given some initial conditions, or conditions at some point, of hydrogen, nitrogen, and ammonia. And we're asked to determine the Gibbs free energy change. Now that doesn't say standard. We're calculating just delta G under those conditions. And then what's going to happen? We're going to look at the sign of that Gibbs free energy and determine what the equilibrium will do. Okay. So this is chemistry. The first thing you'd want to do is write a balanced chemical equation. So I'm going to get that down. It's rare that it's not helpful. So this is the Haber process, hydrogen plus nitrogen makes ammonia. The world's agricultural sector doesn't work without the ability to get nitrogen back in the ground. Diatomic nitrogen doesn't go into soil. But ammonia is a way to get nitrogen into soil. So the world produces a lot of ammonia. Okay. So to answer the free energy, so this is an important part, that we're after the free energy, not the standard, but we need to know the standard free energy plus RT ln. This is not at equilibrium, so RT ln Q. Okay. So the R we're just going to look up. That's on our formula sheet. Temperature, we can grab that from the question. The Q, we're going to have to write an equilibrium law expression. Okay, and we can plug in our values. So this, we have everything we need to plug in the Q, but we need to solve for that delta G standard, and that's why we were given the equilibrium constant. Okay, so we're not going to go to our data booklets. We've got K delta G Now, I'm missing one thing. Delta G is RT ln K or minus RT ln K. We know the K, so we can predict the Gibbs free energy. That's again why that is relevant. So under standard conditions, 1 mole per liter of all the chemicals are 8.314 joules per Kelvin per mole. Times we're 375 Kelvin, and the natural log of 4.3 times 10 to the minus 4. So Kelvin goes, the joules and the moles are still there. So initially I get a positive, and I'm rounding this, 24,000 joules per mole, or a positive 24 kilojoules per mole. So now we've got everything we need. We can plug into the equation on the right. So delta G, not standard. The free energy under those conditions we have in the question, delta G is a positive 24 kilojoules per mole plus RT ln Q, 8.314 joules per Kelvin per mole times 375 Kelvin times the natural log. I'm just going to pull this down. I don't quite have enough space, and I don't want to totally squeeze everything in. So now I've got lots of room. So we're writing an equilibrium law expression. Let's remind ourselves, I want to plug the numbers in, but we've got ammonia, and we're going to have to square that. And the hydrogen, there's 3 of those, so we're going to have to remember to cube that. Nitrogen has a 1 coefficient. So ammonia is on the top, 4.4 times 10 to the minus 3, but because there's 2 of them, we're going to square that. Now I should be putting in my units, but both Q and K's, even if the units don't cancel, K values are always unitless. Q calculations would also be unitless. So for the space, I didn't put in my atmosphere units. I should have, but they don't cancel. Hydrogen, 0.40 atmospheres, that's cubed. And my nitrogen, 0.86 atmospheres to no power. So delta G equals, I'm going to leave the 2 pieces separate. My RT ln Q, we still have, we've got joules and moles left. So I get minus 25,000 joules per mole. or delta G, the standard delta G, we would want to say is endergonic. Under standard conditions, this reaction wouldn't occur. But the RTlnQ piece is so negative that it's overcome the endergonic sort of nature of this reaction, and it is barely exergonic. Okay. The free energy under those conditions, and remember, I just want to highlight how little product there is. Okay. Very low percent reaction, but at this point, the reaction would go forward. It is exergonic in the forward direction, and it would go forward, and it would be soon stopping. This reaction wouldn't go very far before it would get to equilibrium. And then it would not keep going to free energy being positive. That would be impossible. Okay? That would violate the second law of thermodynamics. Okay. So we're pretty much done this lesson. This slide kind of highlights all the skills that you need to practice and assimilate. You've got under, at equilibrium, you can get the standard delta G, or if you know the delta G, you can get the K. You can go back and forth there. Under non-standard conditions, you've got to use this equation, and under non-standard conditions, we don't write K, we write Q. So for practice and the Advantage AP2 Chem textbook, you've got the practice. If you want to, you end up converting from joules to kilojoules all the time. If you use this version of R, okay, you could always just convert R to kilojoules. So this is R again, but it's just divided by 1,000. The joule units have been converted to kilojoule units. And if you use the bottom version of R, which I'll put in green, it's just going to save you that repeated conversion. So you may want to get used to using 0.008314 kilojoules per Kelvin per mole.